We'll further describe the generalization of linear regression with an example. We consider data as shown in the table. In the first column, we have the years. The second column represents the sales done in these years. When you started your business, in the first year, you had sales of something like 651, and you did some advertising, which was you did 23 units of advertising. So the data is given for the first 5 years. Now we want to predict the sales using advertising and the years as predictors. So in any coming year, maybe in the 15th year, how much advertising will result in how much sales. So this is what we want to predict, and we'll use this linear generalization of linear regression to solve this problem. The first thing over here is that we should observe that we have two features. So in the data vectors, we have the amount of advertising that we have done and the year in which we did this, and we want to predict this sales. We have the pseudo inverse. So first thing is to formulate the data matrix. In the matrix notation, we have this is the data matrix X, and in this matrix we have these. The first row represents the years in which you want to predict the sales, and the second row represents the amount of advertising that is being done. Each column is a data vector, and each row represents a particular feature or feature against which we want to do the optimization. Y is your observation vector. So for the first year, you did 23 units of advertisement, and the sales were like 651 units. So forming the matrix X hat, we add a row of ones below the rows of the features, or we add a one as the last element of all data vectors. So here is how we get the pseudo inverse. I have used the dagger sign to represent the pseudo inverse. The pseudo inverse is x hat into x transpose. Take the inverse and multiply it with x hat. The resulting pseudo inverse matrix, you can do the calculation, and this is the pseudo inverse. Now if you multiply this matrix with your data matrix, the result will be a identity matrix. Using the this pseudo inverse, we can calculate the optimal weights, which is represented by W, and multiply your pseudo inverse with the observation vector, with the output vectors, the amount of sales you have done in earlier years, and the resulting matrix is that this. Okay, so for we have W 2 is 109, W1 is 6, and W0 is 391. And now I can write my linear regression model like this. The sales, we want to predict the sales, and the output is Y hat. So the Y hat is 109 times the years, the first element of your weight vector, 6 times the advertisements, and 391 is a bias which is added to these two summations. Uh, in case of a line, we call this addition an intercept, and that is the point where your line crosses the y-axis. So was a simple example where we looked at how pseudo inverse can be used to find a linear regression model for higher dimensional problems.